Hello, this is the next video in the series on testing strategies for the ACS Organic Chemistry Final. So this video is going to be on spectroscopy, and in particular IR spectroscopy and NMR spectroscopy. So the first thing to talk about is the fact that you're not going to get a lot of information as far as the fingerprint regions for the IR or chemical shift information for the NMR, stuff like that. So, but I don't think it's necessarily wise to remember a huge list of things. Although if you want to, you can. Stuff like that. So, but if you know sort of the regions that things are, where things are, you can get a lot of information. Okay. So for IR, I'm sorry this isn't in color, but there's specific regions you can look at. So above about 2500, okay, this is going to be things bound to hydrogen. Okay, so you're talking about like this one here. It's a carbon-carbon, or it's an alkane CH peak. The alkyne, alkene CH peak, I believe, is right there, and then the alkyne CH peak, I believe, is over here, but they're right around in here. The OH is typically like this big broad thing. OH and NH would be a little bit smaller, also in this region, stuff like that. But things above 2500 are going to be things bound to H. The triple bond region is typically between 2000 and 2500. So you're looking at carbon-carbon triple bonds and carbon-nitrogen double bonds. At about 1500 to 2000, you're going to have your double bond regions, and in particular what you're going to be looking at is the 1700 peak, because those are the C double bond O's. Okay, you also have the the carbon-carbon double bonds, and those are typically a little bit lower numbers than that. Your single bonds are over here between 1000 and 1500, and your bending modes are between 500 and 1000. I don't know how useful these are, but certainly above 1500 you can get a lot of information. If you remember where these are, if you remember this region where things bound to H, triple bond, double bond, particularly the 1700, you're going to be doing okay. Something like that. So for the NMR information for the chemical shifts, okay, so you're going to be the regions themselves, the chemical shifts themselves are actually pretty similar, in that if you're just dealing with alkanes, right? So the carbons, right, go from 200 to 200, 0 to 200, some of that. So this is carbon 13. The really small numbers, 0 to 12, right? This is going to be hydrogen. So down here at these low numbers, these are typically saturated. So these are alkanes. Things that are next to things that are next to double bonds are going to be in this region here. If you have electronegative atoms near you, so if this is a CH next to an O, you're going to be in this say 4 region, ppm. It's sort of classic, sort of just like it's about a third of the way down here. Triple bonds happen to be here and here. So the here on the carbon 13, anything with a double bond is here. Now with the hydrogens NMR, it's in things that are on a double bond are in that sort of 5 to 6 region, so with that. So aromatics are going to be in this sort of 6.5 to 8 region. Aldehydes, so if you have the aldehyde H, so this one here, that's classically 9.5 to 10, and then if you have a carboxylic acid, this hydrogen is going to, if you can see it, it's usually going to be at about 12 ppm. So those are pretty classic. So like this one here, it's right off of the benzene, so it's in this region. This one's next to the benzene, so it's going to be right in this region here. This one is next to the oxygen, so it's going to be right around 4. This one's next to a C double bond O, so it's going to be very similar to being next to a carbon-carbon double bond, so it's going to be in this region. And then this alkane one, this is far enough from all this stuff that it just behaves like an alkane. It's going to be down here. So if you sort of know the sort of general things, you'll be okay. Now for the carbon NMR, if you have a C double bond O, it's going to be way down here at a very high number. It's above 160. Okay, so also for NMR, you have to remember about the integration. Remember, the integration tells you how many hydrogens that signal is worth. And lots of times, if they don't give you the actual numbers, they'll give you something that looks like this. and you may have one like this and this. What you're looking for is the height of that from here, right here to here, and then so from here to there. The smallest one is almost always going to be 1 carbon, stuff like that. So in this case, so you say, okay, well, if that's 1 carbon height, you know, you need to have your you know, this is, say this is a triplet, you know, you have that integration, say that's a singlet, stuff like that. So if this one is 1 hydrogen high, that means this one's double that, and so this signal must have 2 hydrogens on it. Not so bad, right? Now for this for the splitting pattern, that tells you how many neighbors there are, and you can always remember it because it's sort of like how you figure out what the splitting pattern is. It's always n plus 1, so you're always talking about neighbors plus 1, right? So with that, so like for this one here, right? It doesn't have any neighbors on it, right? Because there's no neighbors here, so it's plus 1, so it'd be 1, so that makes it a singlet. So for this one, right, it has how many neighbors? Right, it's got 3 neighboring hydrogens plus 1, so it'd be 4. That's why it's a quartet. And this guy here, right, how many neighbors does it have? Well, it's got 2 neighbors, so plus 1, so 3. So that's why it's a triplet. So always remember neighbors plus 1. So, okay. Now remember when you're dealing with these questions, anything having to do with spectroscopy, you don't have to solve the structure. You just have to figure out what it's not. Okay, the answer is there. You just have to figure it out, and lots of times it's easier to start knocking things out. Okay, so for here, so if we ask you which one of the IR spectrum, which of these goes with this IR spectrum, well, the first thing I always do is always look at this this region at 1700. Notice how there isn't anything here. This is the C double bond O. So that means our molecule does not have a C double bond O in it. So if you don't have any, you know, so this one and this one, it can't be that, because if it was one of these, you would have a big signal right here. Okay, so that leaves these two, and this, it doesn't really matter, right? That's the same. That's probably this and that, with that. But this, notice how broad that is. That's very characteristic of an OH peak. So that would make it this one. NH peaks are typically like fairly small. Some of that, they're in this region, but they're pretty small. So with that, so that's what it is. So so for this one, right? So for that, again, we're going to look at the 1700 region. That's where I almost always look. So this is 1500, and this is 2000. If you can't read the numbers, ask the proctor. So by that, so they'll be able to help you out here. So like that. So this is about 3000. This is about this is 1000. Okay, so we're right at so we have a C double bond O in our molecule, and so voila, it's this one, and we didn't have to do anything else. None of the other ones had it in there, stuff like that. So, but notice, but if you want to think about this, right? So there's no OH peak, so we can eliminate that one. There is that 1700, so it's right there. This is that right there is the carbon peak. This is the C double bond O peak, stuff like that. So it has to have both of those. So voila, there it is. Okay, so now for this one, which of these signals, which of these compounds would show two singlets? Okay, so by that among the signals. So this one, not only is it just 2, and since it's a benzene, you got to be careful in that the what you're looking for is equivalence. Okay, so what you can do is you can start saying like these really only have 2 equivalents. So you figure out how many these are, right? So but that's so. So that, oh yeah, so which one of these shows 2 singlets among other signals? Okay, so it's not 2 singlets total, okay, but it's going to be 2 distinct signals. Okay, so you say like, oh well, hey, there's this CH3 here, right? Stuff like that. So, but the problem is, so there, yeah, there's no neighbors, right? But the these guys are going to be the these two are actually going to be equivalent to each other, right? So this will actually be one signal, okay? So and since there's no neighbors, right? Right, this would be a singlet. And you say, wait a minute, hold on, these guys here, right? Normally when we're looking at this, we would these are equivalent and these are equivalent, okay, on the pair position. But since the molecule is symmetrical like this and like this, all four of these are actually the same and stuff like that, and you can't split yourself. So this would also be a singlet, okay? So this one would be, okay? This one, so what about this one, right? This is CH3, right? So with that, so this one would be singlet, singlet, okay? So with that, so this may be it, right? So with that, so here it's singlet and singlet, right? Because there's no plane of symmetry in here, but this one would be a singlet. There's no neighbors. This one would also be a singlet, no neighbors, okay? This one right here, right? This would be a CH2, CH3. Even if we don't even deal with the with these right here, well, you would have these, those, and those, and they're all next to things. So they all have neighboring hydrogens. So at no point could you have any singlets on this one. Now here you would have a CH3 next to with a singlet, right? So for that, because there's none here. There's also some right there. So with that, there's also a methyl here next to something. Now these would also give signals, right? But they all have neighbors, right? So with that, but since it's among other signals, right, the answer is actually probably is going to be this and this, right? This one only has singlet, singlet, stuff like that. So it depends on how picky the questions are going to be. But this one definitely has two singlets. This one definitely has two singlets. This one is two singlets. There's just the integration is going to be on, right? This one is going to be 4. That one's going to be 6. So it depends on how the question goes. Now for this one, so with that, so notice how it's from 0 to 200, carbon NMR. Okay, so for something like this, so this region here, right? This is the C double bond O region. Okay, so we know at least have a C double bond O, which makes sense. It's right there. Now the question becomes how. So here we have signal, signal, signal. Now you can't necessarily get integration information off of a carbon NMR, but you can tell that there's a C double bond O and then three other signals. Okay, so for here, right, you would get a signal here from that CH3, CH2, C, right? That wouldn't show up. This would be a CH, and then this would be a CH3, CH3, but because you can rotate it in space, these are actually equivalent to each other. So this one would have 1, 2, 3, 4, 5 signals, but we only need 1, 2, 3, 4. So this would be 5 signals. So it can't be this. Okay, this one here, right? CH3, CH2, the C, so that's good. CH2, CH3. So this would also give 1, 2, 3, 4, 5 signals, right? So it can't be that. Okay. Now this one here, right? CH3, and then C, and then this would also be a C, and then CH3, CH3, CH3. These guys here are actually equivalent to each other, right? Because you can rotate around this bond, and so each one of these can be in their sort of the brothers' positions here. So there's actually 1, 2, 3, only 4 signals. Ooh, that's good. Here it's right CH3, CH2, C, CH2, CH2, CH3, 1, 2, 3, 4, 5, 6 signals, right? So even here 1, 2, 3, 4, 5, or 1, 2, 3, 4, right? So this is it. We didn't even have to solve what the structure is. We needed to make sure that it has a C double bond O in it, which they all did. But you can just count the signals, 1, 2, 3, 4, and if you know your equivalents, you can knock out this one, and this one, so it has to be this one, and that makes sense. Okay. So for this one here, right, so here's this integration data, here to there, to there, to that, okay? So with that, and so what you can do is, right, we have 4 signals, okay? And notice this one right here. This is a pretty distinctive, this is a pretty distinctive for being next to a carbon oxygen. A signal, right, that integrates to this, right? So with that, so it's going to be but it's also a singlet. Those are pretty easy to pick out. These multiplets here can be a little bit trickier, stuff like that, but the singlets are generally okay to find out, or to find. Okay, this one, notice how this one does not have an O on it. It's not an ester, stuff like that. So it's probably not going to be this one. So we're looking at this one, and well, we can get rid of this one as well, because it needs to be, because it's in this region, it needs to, the signal, the CH or whatever it is, needs to be next to an oxygen. Okay, so we're down to here and here. Okay, so this one is a CH, right, with CH3, CH3. So this one would actually have, right, this would have 6 neighbors, right? So it'd be a septet. That is definitely not a septet, and so it can't be this one. So it has to be, by default, be that one. Okay, if you look at the integrations, this should be, so a little bit hard to see, but this one, maybe I drew this wrong, and this is the problem with the integration, is it should probably be like, this should be like 1 to 2 to 3 to 6 or something like that. So with that, so maybe this one's hard to see. Maybe it's only like that. So maybe it's 1, 2, 3, 6. It's kind of hard, especially when the picture is only this big. So with that. But if you find your singlets, you look at look how many signals there are. You can get away with not having to completely solve the structures by figuring out what it's not. Now for this one here, right? So this is, if this is 1 carbon, right? So it's this. This might be, this might be 3 hydrogens. I'm sorry, 3 hydrogens. This is probably, say, that, right? It's probably 9 hydrogens, right, from the height. But also there's only 3 signals. Okay, so these are going to be equivalent to each other. Here's a signal. Here's a signal, signal, signal. 1, 2, 3, 4, 5. Oh, can't be that. But this one here, right, these are all signals. Now this one's not going to give a signal, right, because there's no hydrogen there. Okay, but there's a signal, signal. Now this one only gives 3 signals. Okay, this one have 1, 2, 3, 4, 5 signals. Here, again, you're going to have this T-butyl group is going to be, each one of these is going to be, they're all equivalent, so it's going to give 1 signal. There's no signal there because there's no hydrogen, and then 1, 2, like that. And then here, these 2 are equivalent. There's nothing there. There's here, and then there's that right there. Okay, so this one has three signals. Okay, so we've at least eliminated this one here. Okay, and notice how this one looks a lot like that one looks a lot like a singlet. Okay, now it is hard to tell on this what exactly is going on, stuff like that. But this looks like it's a 9 hydrogen singlet, which looks a lot like a T-butyl group. Okay, so that's what this would be, right? So there's 9 hydrogens with no neighbors, because the neighbor would be right here. So we can get rid of this one, stuff like that, because this one would be 6 hydrogens with a neighbor. This doesn't have a neighbor, but it's only 6. So that would have to be like, the integration would have to be like that high. So but that's, so now we're down to here. So now the question becomes, right, so this is a CH3, and this is CH2. So here, this is definitely, if this was CH2, these two would have to be the same height for the integration. They're not. It's 1 to 3, so it's got to be that one there. And so you sort of have this crazy logic problem saying, what is it not? Well, it can't be this one, can't be that one. Can't be this one because of the number of signals. Can't be this one because we don't have one that goes to 9. So these two have one that goes to 9. It's a singlet. So then is it 2 to 2? No, this one's lower than this one, so it must be 1 to 3. So if you look at these integration numbers, there to there to there. Okay. Now for this one, there's mass spec. So with that, so the fragment, so with that, so which compound would show the major fragment ion, this and this? Okay, so good rule of thumb is that you're going to split next to, on either side of the C double bond O. Okay, so with that, so it would be split here and here. It would split here or here, right? So you're going to have one that's this size and one that's that size. Same thing here. You can have one that's that size. Let me do this in different colors. One that size, one this size, there. One that's that size, size. Oop, sorry, it's gonna split right there. It's gonna split on either side of the double bond. Okay, so for here he has a 127 and a 29. Okay, so for here you would have right. So here you can always do the smaller piece, right? So this would be hydrogen, right, plus carbon plus oxygen, right? So this would be 1 plus, what is it, 12 plus 16, right? So this would be, so this would be equal to 29. Ooh, there you go. So like that. So if you had an extra carbon in here, you know, things like that, this part would be too big. And if you had this one, 1, 2, 3, 4, 5, 6, 7, 8, right? So I would imagine that if you added this up, it'd be 27. So this is the answer here. So always you want to do sort of the smaller side, and you just add it up. So you're going to look at a fragment like this, and then a fragment like that, fragment like this, fragment like that, fragment this size, fragment that size, fragment that size, fragment that size, and you can just start adding them up. If they give something to, if they actually give you a mass spectrum, there is the what you're looking at is the very highest peak with that, and that one will give you the you have to just match up the molecular weight to whatever that littlest peak is. Also, you can look at isotopes. So bromines, right? They give 2 isotopes, and it's sort of 50-50. Chlorine, it's 75-25. So these would be, you'd have 2 peaks that are equal, and then this one would be like 1-to-1. This one would be 3-to-1, the ratio height, stuff like that. So this is the other thing for isotopes, that if they ask you about that, stuff like that. So okay, good luck.